Good morning. Thank you, Jörg. I'll try to stick to the time. So I'll talk about strain effects in altermagnets for the most part. In the first part, I'll talk about manganese telluride and about the spin splitter effect, which can be induced either by strain or actually spin-orbit coupling as well. And as a bit of an aside, I'll talk about spin splitter effect in anisotropic ferromagnets, which, although not altermagnets, turn out can give us the same functionality, which is interesting to have in mind. And then I'll talk a bit about piezomagnetism and altermagnets. So just by way of motivation, since I'm talking about the spin splitter effect, I feel like I have to say why we're interested in that. So the motivation for that primarily comes from the ability to generate transverse spin currents. For devices that could replace spin-orbit torque bits like this, so in those devices we have a charge current flowing in the plane through a non-magnetic material, and through a spin hole current there is a transverse spin current that is absorbed by a ferromagnet and exerts torque on it, and you can switch the magnetization, so potentially implement magnetic random access memories and do a lot of other interesting things. So in this case, the material parameter that determines the functionality is the spin hole conductivity, and it's generally an anti-symmetric time reversal even tensor. It reduces to a scalar in an isotropic material. But one of the consequences and limitations of this is that in an isotropic material, the spin polarization corresponding to the spin hole current is in plane, at least without symmetry breaking. So you cannot switch out of plane magnetization, which is the preferred orientation for applications. And in addition, because it's driven by spin-orbit coupling, the efficiency tends to be quite low. So with the spin splitter effect, which was originally proposed for altermagnets here in this paper, so you can generate transverse spin current thanks to the spin split band structure without any spin-orbit coupling. And here the operative tensor is the spin conductivity, which is symmetric and time reversal odd. So it would change sign if you switch the magnetic order parameter. We can characterize the efficiency by the spin splitter angle, which is the charge to spin conversion ratio, transverse spin current divided by the charge current. And the advantages for applications is that first of all, the efficiency can be larger because it does not require spin-orbit coupling, but also the spin polarization of the spin current is along the Niel vector, which can have a perpendicular component, which is favorable for switching perpendicular magnetization. And then, given that our source is magnetic, so we can couple to the net magnetization, which can exist either intrinsically or could be induced through the piezomagnetic effect. So in terms of materials, if we look at altermagnets, there's really not that many, as you know. Originally, ruthenium oxide was the poster child, and the prediction based on LDA plus U gave us something like 30% efficiency for the spin splitter effect. Unfortunately, it turns out it's non-magnetic, so we have to look for other materials. There's a new group of those Lieb oxychalcogenides. There was a lot of discussion yesterday about those. So those are quite promising in this regard, but so far unexplored. On the other hand, we have G-wave altermagnets, and those are well established: chromium antimony, manganese telluride, reasonable Curie temperatures. But in the G-wave altermagnet, at least without spin-orbit coupling and without the strain, the spin conductivity tensor by symmetry is exactly zero. So no matter which direction in the crystal you send the charge current, it's unpolarized and there is no transverse spin currents. I will use manganese telluride as a case study to show that, in fact, already with spin-orbit coupling with in-plane order parameter, it becomes effectively D-wave, but only weakly, so not strong enough for applications and devices like I described. But with proper symmetry breaking strain, you can induce a very strong D-wave character, which can generate strong spin splitter effect. So let's talk about that. So first of all, what kind of general symmetry effect we're talking about. So we're interested in the response of the spin conductivity tensor to the strain. So it's determined by a fourth rank tensor. So in the non-relativistic limit, it's all easily tabulated. So for all the spin-Laue groups where this tensor is forbidden without strain, meaning G-wave and I-wave, you can work out the non-zero coefficients. So this is the spin group corresponding to the manganese telluride. So there are two coefficients. We will focus on this one. So basically, you apply the strain in the plane, the shear strain that breaks the threefold axis, and we generate the corresponding off-diagonal component of the spin conductivity tensor. So first of all, this is just you could say a test calculation. A few materials simply use a Boltzmann approximation with ab initio band structure to estimate the magnitude of the effect. So there are a few materials here. They're coupled tetragonal, chromium, antimony, manganese telluride. So normally what you would expect is, given that strain is dimensionless and the splitter angle is also dimensionless, so you have two dimensionless quantity, the ratio of those should be of order 1 in a typical system. And it is of order 1, so you see everything except manganese telluride, 1 or 2. It varies with the Fermi energy, but it's of order 1 as expected. But in manganese telluride, it comes out much larger. So this ratio, you see it's factor 0.1. So it's a few dozen, actually. So where does it come from? This is what I am going to explain. No, the other ones are metallic. This is important, yes. All of these, except for manganese telluride, are metallic. So this kind of plateau here is one of the signals that it's a semiconductor. So there's a valence band maximum here. This is a reminder of the band structure. So it's a hexagonal nickel arsenide structure. And the valence band maximum is at the A point. There's a nearly quadruple degeneracy. There's a tiny splitting into doublets there, which I'll mention later. This is a band structure from a GW paper here. It's slightly above gamma, so it's known that by varying the C/A ratio, one can tune the relative position of the gamma and A points. This was also shown in this paper, but we will assume that the band maximum is at the A point. Now, the important point here is that there's extra degeneracy here compared to what is required by a minimal model for it to be an altermagnet. There's an extra orbital double degeneracy. The bands are formed by tellurium, px and py character. So that extra factor of 2. And it's very important for the spin splitter effect here. So here, this expression gives the KP model that is derived from symmetry considerations. There are a few different terms here. So the first line is the non-magnetic, non-relativistic terms. So it simply describes heavy and light hole bands. And then the terms shown in different colors can be determined from come from different sources. So the blue term here, that's the altermagnetic hybridization via manganese. And this can be derived from the spin group, right? It's a non-relativistic effect, so there's a sigma z here, but that's the z that is parallel to the order parameter. The green terms are spin orbit terms. And they're derived assuming time reversal symmetry is present. So there are 4 of them, actually. There are 4 of the 4 terms, and the k is the wave vector, but the tau and sigma are the Pauli matrices. And one of the Pauli matrices corresponds to the orbital doublet. That's the px and py. There's another term here that may need to be included in some cases, but it's actually tiny. That's the term that is not covered by these 2. So note that this comes from altermagnetism alone without spin-orbit coupling. This comes from spin-orbit coupling in the presence of time reversal symmetry. So it doesn't know anything about altermagnetism. And those terms, for the most part, are sufficient to describe the band structure. With the only exception of a tiny splitting here, which is about 2 millivolts that you can't even see on the scale. So that term is the additional spin-orbit coupling, which is induced by magnetism. So you can describe it by this term, then it fits essentially perfect. So what you see in the pictures are band structure, are eigenvalues obtained from ab initio. So each point is a first principles eigenvalue. And the lines are the fits to this Hamiltonian. And this is in the nodal plane. So black color means they're spin unpolarized. And this is slightly shifted away from the nodal point, from the nodal plane in the z direction. And here they do acquire spin polarization as we move away from the A to gamma line. So you see the KP model with the fitted parameters gives a very good description of the ab initio bands, including their spin polarization, even though the spin polarization was not part of the fit. Only eigenvalues were fit here. So if we look at the whole isosurfaces, so now we cut through those bands slightly below the A point at a reasonable hole concentration. So without spin-orbit coupling, we have pure spin-up and spin-down bands. So the blue and red would be spin-up and down. They form this G-wave pattern, and they're completely independent of each other. If we include spin-orbit coupling, then spin-up and spin-down get strongly mixed. In some regions, they're quite broad regions where the spin polarization is very small, so spin-up and spin-down are strongly mixed. But the interesting feature of this band structure in manganese telluride that close to the A point, in fact, there is no transverse spin texture. So there is some if you move away from the A point, but one could call it persistent spin texture. And there's an underlying reason for that. Essentially, spin gets entangled with the sublattice degree of freedom. So the basis functions at the A point have 0 matrix elements for the transverse magnetic field operators. So they don't generate any transverse components. 2 leading orders. So now what happens if we add strain to the system? Generally, all of those terms can become anisotropic. All the hoppings can become anisotropic. But it turns out that to describe what happens to the band structure, it's sufficient to add just one term, which splits the px and pz orbitals. Remember, tau is the Pauli matrix acting on the orbital doublet. So px and py are the basis functions. So their energies are degenerate in the unstrained case because it's hexagonal. As you apply the strain, you lift that degeneracy. And the strain is assumed to act like this. So it distorts the hexagon. It's epsilon xx or minus epsilon yy. So it introduces a crystal field splitting that is proportional to the strain. So this parameter will be proportional to the strain. And as you see, the comparison of the band structure under strain from first principles agrees with the prediction of this model where we just add this term here. And the term is about...
Question?
Sure. Microphone?
should I understand correctly that this delta S means that the length of bonds coming from tellurium becomes different for sublattice 1?
Here, this just means that px and py orbitals are split in energy. So it's true that the hybridization will also become anisotropic, but it turns out that it's not important to include that splitting in the Hamiltonian, because this one single parameter is already good enough to describe what happens to the band structure. So this is the crystal field splitting here. And it may be a bit difficult to read this plot, but here two sets of bands are shown. So one in the nodal plane relative to the containing the A point. So that's the black bands here, and they are black because it's a nodal plane. And the other set is shifted for K shifted in the Z direction. So this is without the strain, and this is with the strain. So you see what happens both in the nodal plane, and in the nodal plane you see the splitting, and this 21 millivolts is essentially the splitting at the strain value. But everything still fits quite well, so it's a faithful model in the presence of strain. And here's what happens to the isosurfaces. So this is what we had at zero strain. It does appear to preserve the G-wave character. It doesn't quite preserve it because of the spin-orbit coupling. I'll say a bit more about that later. But it's not exactly G-wave here. It looks like G-wave. But if you apply strain, it clearly doesn't look anything like G-wave. This is a clear D-wave character. In the YZ plane, we should expect a spin splitter effect. Right? If you send current this way, for example, there should be spin current flowing that way and the other way around. And you change the sign of the strain, the distortion changes direction. Now the sign flips to the opposite. So we can use the Boltzmann approximation to calculate the spin conductivity tensor and the spin splitter angle, defined like that, as a function of the chemical potential. It's a 0 is at the A point. So the valence band maximum, because of spin orbit, it's slightly shifted, maybe 30 millivolts above the A point, small on this on this energy scale. So we see that, let's say, this shows the magnitude of strain in percent. So at 1% with a chemical potential close to the top of the valence band maximum, we get something on the order of 0.3. So this gives us a gauge factor of more than 30. That's consistent with what I showed before. It would be more than 100 if we turned off spin-orbit coupling. So that mixing that is introduced by spin-orbit coupling reduces it a lot. But still, despite that, the gauge factor is huge. It's more than 30. Remember, in metals that I showed on one of the first slides, it was an order of 1. Here, it's a factor of more than an order of magnitude enhancement. So the physical mechanism here, of course, is that we have this crystal field splitting. And when the Fermi energy is in this region, it gives a very large distortion of the band structure, as we've seen here. Now, if you look very carefully, you'll see that at zero strain, this is not exactly 0. We can blow this up. And at the band edge, it's on the order of 0.02, so 2%. It's quite small for applications, but it's still noticeable. And remember, I told you that if we look at this isosurface, it doesn't look like it's reduced from G wave to D wave. But if we look very, very closely, close to the band edge, this is 1 millivolt below the band edge, we see multiple values here. And in the structure of those values, it's clear that it's not G wave anymore. So thanks to the spin orbit alone, right, because we have an order parameter in the y direction, it's lying in the plane. In the presence of spin orbit, the symmetry is reduced to orthorhombic, I guess. So there's going to be, if we move really close to the valence band maximum, there's going to be 8 valleys, and each of them will be spin polarized. There will be 4 blue and 4 red valleys, and it's clearly D wave. So the spin-orbit coupling also effectively reduces the spin momentum profile to D wave in the YZ plane. Tomasz was showing some recent experimental measurements that appear to be consistent with that. But this is, of course, totally expected.
May I ask, once we are here, this D wave usually shows this 90-degree symmetry. So if I rotate 90 degrees, then the sign of the effect and the polarization of spin current should swap. So what is this angle here? Because you start from the 60-degree between equivalent directions.
Yeah, so in the YZ plane, there was never a 4-fold axis. There's only a 2-fold axis. So it corresponds to an orthorhombic symmetry. So it's not D wave in the same sense as in tetragonal, but we call everything D wave where the spin conductivity tensor is allowed.
Okay, I will ask like experimentalists. So if I would like to prove this altermagnetic effect, the first thing I do, I tried to probe different directions and see this inversion of the sign. So this I cannot get in antiferromagnet, in ferromagnet, only in altermagnet. So is it an angle through which I should rotate? Because if you have 6...
Here it will be symmetry planes, mirror planes. So like imagine a mirror plane going here, here, there. There would be a spin flip coming with those mirror reflections.
So I was wondering the same thing. So this plane, if you send a current, it will not be spin polarized, right? In this plane.
No, it has to be in the YZ plane.
Yeah, exactly. It has to have a component along Z.
Yeah, so presumably, I mean, this calculation here, it assumes charge current along the Z-axis and the spin current along the Y-axis. So I actually have a picture here showing what you would want to measure, one option what to measure. So you would have some sort of substrate that would break the 6-fold axis. So you have to grow it with the C-axis in the plane. And then you would have, this is the Y-axis, so you would have a spin current flowing up and into the free layer, or perhaps you could absorb spin accumulation at the surface with MOC, something like that. Yeah. Formally, the magnetic point group with the order parameter in the plane is orthorhombic. It's no longer hexagonal, but it's, of course, not tetragonal either. Okay, now a bit of an aside, because it's not about altermagnets, but do we actually need an altermagnet to get the spin splitter effect? The answer is no. You can get it in a ferromagnet as long as it's crystallographically anisotropic. So imagine we have 2 different Fermi surfaces for spin up and spin down, and they're totally different. There's nothing that takes one to the other, but still you can grow a film with the tilted axes, and then it's easy to figure out that if you impose the open circuit boundary conditions, so you set the charge current to 0, there will be a finite spin current. And the spin current is proportional to the difference in the spin polarizations along the 2 principal directions of the conductivity tensor. There's a geometric factor that contains the tilt of the axis. It's maximized when it's 45 degrees. But the main materials parameter is this different spin polarization along the 2 directions. It doesn't have, they don't even have to have different sign. They just have to be different. Just a simple calculation shows that the main factor controlling that difference is the difference in the what's called a plasma frequency tensor. We can, in the first approximation, forget about the spin dependence of tau. It modifies the polarization factor, but it doesn't change sign. It's mostly proportional to this. And that can be easily evaluated from band structure. And if we do that for a range of ferromagnets, all of these are anisotropic ferromagnets, tetragonal, hexagonal, orthorhombic. This is the value of the spin splitter angle that you'll get from that formula. And typical values are on the order of 0.1, 0.2. So about a third have more than 0.2. So this is quite competitive with platinum as a spin Hall source. Similar order as you would get with ruthenium oxide if it was magnetic. So this is an option that should be entertained. It's you lose some advantages of altermagnets in terms of speed of switching, perhaps, and stray fields. But as a spin current source, this could be competitive. So now I'm switching to the last topic, which is piezomagnetism.
3 more minutes, right? Unless he gives you more.
I humbly request. I don't think I can do with 3 minutes, but I probably just yeah. So this was done in collaboration with Maxim Khodas, Saimiu, and Igor Mazin. The standard treatment of piezomagnetism is based on magnetic point groups. This has been done decades ago. You can pick up this book from 1964, and there are tables for all magnetic point groups where you can read off what the allowed components of the piezomagnetic tensor are present in those point groups. They're given in this partial Foyt notation. 1 to 6 means 6 different components for the strain. That's the 6 columns. The rows give mx and y, mz. So, for example, a Q31 here means that there's a that ZZ strain generates mz, and often there are relations between those two. So I just wrote the ones that correspond to familiar altermagnets like manganese telluride, chromium antimony, and rutiles with the actual orientations of the order parameter L. This is all well known. Same tensors determine strain-induced anomalous Hall conductivity. You just do a dual transformation from the M component to the dual component of the tensor. I mean, this can be the anomalous Hall vector instead of M. Same components. But the disadvantage of this description is that the tensor is tied to a specific orientation of L. So you rotate the L, your magnetic point group changes, and you no longer know anything. So for generic direction, symmetry is reduced. You look up different entries, and there's no connection between them. There's also no insight into which terms are large or small. You just get which ones are allowed, and that's it. And it doesn't tell you anything about the mechanisms of piezomagnetism. So an alternative approach is to start with the spin point group, which allows L to take an arbitrary orientation, and see what we can deduce from that. Now, let me just briefly point out that when we talk about non-trivial spin point groups, there are alternative languages which mean exactly the same thing. So in collinear magnets, the non-trivial spin group is equivalent to the Shubnikov's black and white antisymmetry group, as it was pointed out by Turek in detail. So this is, unfortunately, Shubnikov's work is somewhat obscure because all of those papers and books were published in places like Trudy, Akademie Nauk, SSSR, which is if you want to bury a body, that's where you go. You can't find a more obscure source. But they were published in a book, and in translation in '64, and I mean it's known, but not as widely as magnetic point groups. But Shubnikov never worked with spin vectors. It was always anti-symmetry, black and white, dichromatic space groups. They all mean the same thing. So these are the pictures from Shubnikov's book from 1951. There are no spins here. It's just colors. So this is an anti-symmetry mirror plane. This is a fourfold rotation with anti-symmetry. So all of the space groups and point groups derived by Shubnikov and his students were based on anti-symmetry, and they're 1651. They're all isomorphic to magnetic point groups. They're derived in the same way, but those are different for a given system. And the non-trivial spin group, that's part of the full spin group for collinear magnets, is identical to the Shubnikov black and white group. It basically tells us of the two sublattices which one is where. And on the other hand, there's another approach popularized by McClarty and Rao's paper, where the spin ordering is designated by picking an irreducible representation of the point group, of the crystallographic point group, a one-dimensional representation, giving the symmetry of the spin splitting.
Real representation. Real representation.
Yes.
A one-dimensional real representation.
Yes, correct. All characters are 1 and -1.
For those representations.
Yes, and it contains.
No. That's been known for ages, right? Yes.
Yeah, and what I want to point out that it contains the same information as the non-trivial spin group or the anti-symmetry group. It just tells us which spins are black and which spins are white. And there's a simple correspondence because the one-dimensional irreps define halving subgroups, and they treat L as a scalar, which essentially becomes black and white. And elements with character -1 come with color swap in the anti-symmetry group. So it's a direct one-to-one correspondence. So when I say non-trivial spin groups, someone else could say we pick an irrep, same thing, just a different label. So first we can consider the non-relativistic limit and see what kind of free energy invariants are allowed by different spin-Laue groups. So spin-Laue group, you take the spin point group and you add inversion, because inversion has no effect on the piezomagnetism. So in this case, the induced magnetization is always parallel to the order parameter, and then different spin-Laue groups differ in the function of strain that enters into the invariant. And this tabulates all of them. It turns out that in D-wave altermagnets, the response is linear. And these are the allowed components. Rutile, Lieb lattice, they belong to this one. So the XY is the only strain component that will induce magnetization. G-wave are all quadratic. Manganese telluride and chromium antimony fall into this category. And I-wave, of which I actually don't know examples, don't remember, they're cubic. One other point to make, that in some cases, if the material is insulating, then in the non-relativistic limit, strain will actually not generate any magnetization because of what Igor Mazin likes to call Luttinger compensation. Basically, you have an integer charge in every band. So if you split the bands and they're all filled, you still get 0. But you could still observe splitting at the gamma point, which is described by the same invariance here. So you could spectroscopically look at the splittings. So this is the non-relativistic limit. Now, of course, the non-relativistic linear terms should typically dominate. But in G-wave and I-wave, where non-relativistic starts with second order or third order, it's likely that at least at small strain, if there are linear terms coming from spin-orbit coupling, those should dominate. So we can then look at bilinear L.M invariants that are allowed on the strain in all the same groups. And this consideration can use the same non-trivial spin point group. Those allowed at 0 strain have been already tabulated in this paper. I think Brian discussed that yesterday. And there was one important point that the terms that contain cross products of L and M come with leading order in spin-orbit coupling, so they should dominate. So this, of course, carries over in the presence of strain. So the way they're tabulated here to save space, C alpha beta is a product of L and M components, and plus is a symmetric, and minus is an anti-symmetric combination. So the anti-symmetric combinations come from the cross product, and they come with first order in spin-orbit coupling, so they should dominate. So this lists all the allowed terms in the presence of strain, where there are some in the absence of strain. Only those that generate new components of the magnetization are listed here. And you can always generate all the missing components by strain. If only some are allowed without the strain, you can generate everything else. So common examples are listed here. So the anti-symmetric terms actually correspond to strain-induced Belashchensky-Marie interactions. So they would induce canting as opposed to the longitudinal magnetization. Now notice that here, because of the way they are constructed, they automatically include all the angular dependence. So we're not tied to a particular orientation of L. We can work out the entire angular dependence if needed for the magnetization induced by strain. So I want to show an example comparing what we can get from magnetic point groups and from this consideration based on spin groups. So this is an example for 2 altermagnets, chromium, antimony, and manganese telluride, which, as altermagnets, they are siblings. They're very similar, same crystal structure, same magnetic order, with the difference that the order parameter is along in different directions. So in chromium antimony, it's along the hexagonal axis. In manganese telluride, it's in the plane. So the magnetic groups are totally different. Chromium antimony is hexagonal. Manganese telluride is orthorhombic, as I mentioned. So this is what you get from those tables in Burr's reference manual. 3 non-zero components, they are related to each other. I mean, it's only one independent component for chromium antimony. In manganese telluride, 5 distinct components, and that's all we know from the magnetic point group. Now, the spin-Laue group is the same. The spin-Laue group doesn't care about the direction of L. We know that in both, there's no linear piezomagnetism in the non-relativistic limit. There's a quadratic term. But they're linear L.M invariants. And there are 3 of them. There are 2 here because there's a plus minus. We can explicitly write them out and specify what they mean for a particular orientation of L, here along Z, here along Y. So here, then we can read off which tensor components are allowed. So LZ is essentially 1, because that's the actual direction.
Minute 40, right? You decide what we're doing. I'm just reminding. Minute 40.
Thank you. Yeah.
No stress.
Actually, I think there is stress.
I am so ashamed. Yes, we are under stress. So, for chromium antimony, we get the same tensor structure as from the magnetic point group, same elements that we read from here. For example, XXY, it should be one of these. But what we now learned that is new is that it comes from the term that is antisymmetric. So DMI contributes to it. Linear and spin orbit coupling, it can be large. We didn't know that based on magnetic point group. Now in manganese telluride, there's actually quite a lot new stuff that we learn. So there's a relation, there are two relations between different components. Here we only had 5 distinct components. Here we know that to this order, to linear order in L dot M, there are 2 independent parameters. So pairs of these are related, and one of them is absent. We know that DMI contributes to lambda 2, but not lambda 1, so this should be much larger in principle than lambda 1. And the ZZZ is 0 to linear order in L, which is kind of obvious because epsilon ZZ does not lower the hexagonal symmetry, and we know there's no linear invariant at 0 strain, so it shouldn't appear either. So we learned quite a few additional pieces of information from spin group analysis. So this is my last slide, where we try to classify. I'm not sure why this shows up. Sorry about that. So we're trying to classify different mechanisms contributing to the piezomagnetic response. So there's, of course, a band filling effect, which when you break the symmetries connecting spin up and spin down bands, then simple band filling will give you finite magnetization. This has been noted before, one example for oxyselenides in that paper. But here I show a quadratic piezomagnetic effect in chromium antimony. This is a first principles calculation where we have 2 strain components. There's a in-plane share and a YZ share. They are applied here, and then you have a quadratic surface showing the magnetization. The coefficient here, you can't see it, but it's negative 39 Bohr magnetons. So multiply by epsilon squared. That's what you get. There's a thermally driven.
You need coffee, right?
Yes, I know. Okay. I'll just wrap up. There's a thermally driven effect. If someone is interested, just talk to me later. In the mean field, it's basically a product of the sublattice susceptibility of the magnetic susceptibility and the sublattice magnetization, which has a maximum just as in the magnetoelectric effect. And the coefficient comes from the splitting of the exchange of the 2 sublattices. And there's a DMI-induced tilt of the spins that gives a transverse response. So there are some calculations there, unfortunately, very few experiments.
Keep that slide on, because, sorry, as an experimentalist, I won't like to object. So, cobalt fluoride, classic piezomagnet, right? So it's a collinear structure, high symmetry, direction, it spins along c-axis. So spin group analysis and magnetic point group analysis give exactly the same result, same tensors.
Mm-hmm.
The piezomagnetism is entirely longitudinal. So it's basically becomes a ferrimagnet. So it's not true this is
No, this is not true.
It is true.
It is not true. It is. No, this is not true.
It is true.
It is not true. It is. No, I guarantee you, it is not true.
Cobalt fluoride.
No, it's not true. It's not true.
It is true.
No, it's not true.
I promise it's true.
Look at Borovik-Romanov's review. There are 2 coefficients. There are 2 independent coefficients.
No, wait a second. No, one thing.
Okay.
One point I want to make. There is a longitudinal component.
Yeah.
And that longitudinal component, there is a longitudinal component.
3,6. That's the longitudinal.
Yeah, 3,6. There is a longitudinal. And that longitudinal component is entirely due to spin-orbit coupling.
This is not true.
It is true. Because it's the other mechanism, which I discussed it with Igor, the other mechanism that is the thermally induced effect.
Mm-hmm.
So basically what happens is that the 2 sublattices become inequivalent, and the reason why they become inequivalent is spin-orbit coupling. There's no other mechanism. There is a possibility of a thermally induced effect in cobalt fluoride, but the piezomagnet is maximum in low temperature.
Agree that this.
So I don't disagree with
Yeah.
any of this,
No,
but we
yeah,
should point
I-
out that sometimes
yes.
things are more subtle.
There was another question.
Agreed. Agreed. There are two components there.
You
Yes.
agree?
But there's also a transverse.
Switch up.
So thanks for the nice talk. I'm really curious when you showed this spin splitter effect with this anisotropic ferromagnetism. So I can decouple it like an altermagnetic plus an uncompensated moment kind of thing. And the spin splitter current is actually coming from the altermagnetism. Like if I want to break it down, like an equally compensated red and blue, and due to some perturbation, the moment compensation is not happening. But the actual spin splitting effect is coming from the altermagnetic part. Am I correct? Like you showed that other than altermagnetism, you can.
I wouldn't. So you see, all of these are ferromagnets, right? I don't know in which sense. Let's say, I don't know. Iron to boron could be called an altermagnet with a slight. It's a conventional ferromagnet.
That's true because.
It's just anisotropic.
So my point was that this altermagnetic symmetry is actually not an essential feature in the spin splitter effect. The essential feature is that you have two different Fermi surfaces with different anisotropies.
It's not an order parameter. It's just not
Correct.
an order parameter. So
Yeah.
it's, in the strict sense, you can call it D or S, but
No, it's just anisotropic.
Yeah,
Okay, so
Okay,
why don't you
thanks.
finish the talk? And then we have a few more questions, but then we need to get coffee.
that's very generous, but I think I pretty much finished that because we.
Thank you very much. Questions?
Yeah, thanks. Very nice talk. So could you put up maybe the penultimate slide again, where you basically compare the LM classification with the magnetic point group?
You said penultimate?
I think it was.
With a table, yes.
Yes,
I,
yeah, the
I,
table,
I know
yeah.
what you mean. Yeah.
Yeah, so could you maybe explain what additional information is somehow coming in the PM tensor from L dot M that wasn't there in the magnetic point group classification? Because it seemed to be both symmetry-based arguments, but one gives more than the other.
Right. So we get more from spin groups because, first of all, we have a separate non-relativistic and relativistic description. And in addition, we have a description that allows for an arbitrary orientation of L. So you see here, Lx and Y and Lz could in principle take any value. So you can say how your piezomagnetic magnetization would depend on the orientation of L. It will be some geometric function that you could check experimentally. In addition,
So if you were able to twist it out of its actually thermodynamically allowed position,
Yes.
that's the statement.
yes,
Okay.
yeah, you could do spin flop and rotate the magnetic field, for example. You would have the angular dependence from this. In addition, you learn more about the coefficients themselves, right? So here you don't learn anything more about the structure of the tensor, but you know that it's linear in spin orbit, so you expect it to be large. Here, instead of 5 coefficients that are all distinct on the magnetic point group level, we get 2 relations for them, right? One of them is small, which we could guess, but this formally tells us that that one is 0 on this level, on the linear level. But there are relations between these two. So xxz and yyz, here, they were just different. And nothing to be learned about those. Here we learn that they are actually on the bilinear level. They're opposites of each other. And it's also small because it's not an antisymmetric term. But there's another pair, also distinct here, nothing.
But so is it true that that so basically my question is here. So my right. So my question was, what you seem to be asking is, I have a piezomagnetic tensor, and I'm using symmetry arguments to determine which coefficients can be non-zero and how many different I have. Then you have two approaches for doing that. One is, or was done, magnetic point group, and I just don't see how the second thing is fundamentally different.
Okay, I can explain. So essentially, is that okay? Sorry. You can.
If you,
In every talk, yeah?
I know two people who do that. Igor Masu.
Why don't you answer the question and then everybody can comment, including Hyro?
Yes.
Yeah.
Maybe I'll try and then.
Yeah. I think you'll do a better job than I do.
Try.
So there are two differences. One difference is that from the beginning, we don't fix the orientation of L. Right? When we derive the invariants, they come up in a way that contain products of L and M. So the resulting invariants carry over regardless of which way L points. Magnetic point group cannot do that in principle. That's one thing. The other thing.
There's a reason why I cannot do it, because it's not allowed.
Of course.
To twist it out of. I mean,
Well, no, it's not because it's not allowed thermodynamically. It's because you fix it to a symmetry direction.
Oh, magnetocrystalline anisotropy makes a decision here, right?
Yes, can I just pitch in this business of the complementarity of the two analyses, right? So basically, you have a tensor that is allowed by the magnetic point group. That's all that there is allowed. This tensor can be formally decomposed into two parts. One, it is co-rotating in collinear altermagnets. One is formally co-rotating with the staggering magnetization, and it's always collinear with the staggering magnetization, and everything else. That part that is co-rotating, by definition, is allowed without spin-orbit coupling, and it has a higher symmetry. And then the rest of the part describes the non-altermagnetic textures. So that the sum of the two still has the full magnetic point group symmetry. So the highest. So you can think about the first part as a scalar tensor multiplied by staggering magnetization, and the rest is whatever else is allowed. So because the scalar part has a higher symmetry, then you have all these other properties in which coefficients become coupled, etc. Right? So that's all there is to it.
It's slightly more complicated than that, but you're right. If you fix the orientation of L, whatever it is, what you learn from this, the allowed terms will be exactly the same as from the magnetic point group, but you may know some additional relations between them that hold approximately.
It's co-rotating with that. So if you rotate L, the prefactor remains the same. The only thing you rotate is the direction of quantization.
You would have a co-rotating part, which in the non-relativistic limit, you know what it is.
Exactly.
With spin-orbit coupling, it's not really co-rotating, because it will depend on the
residual part that is not co-rotating.
Yeah, but here, like in these two cases, there is no non-relativistic part at all.
Right.
It's all relativistic.
Yeah, of course. Yeah, at the lowest order it is, yes.
Okay, so maybe, does it care to listen or not? Okay. So maybe I can tell you a little bit of what is important that is different in there as well. From a spectrum point of view, they are not inconsistent with each other. And the magnetic group is going to tell you, look, they're all just different. The other group is going to tell you that there's some relations. If sudden you see that two of your responses are very large, and typically they are going to tend to be, because the exchange origin will tend to be much larger than the other components. So if you guide magnetic group would never by definition allow you to tell you that there are any relations between them. So the aha moment of saying that spin symmetries or spin analysis was telling me yes or no. In this case, it gives me a hint of the possible magnitudes, because in here it gives me a relation that these components are related and can be large if the measurement allows it. So you do the measurement, you see this, oh, these are very large, but the magnetic group would have never told me that they're related. That's where the complement is coming.
This is a
Thank you,
very
Franco.
interesting discussion. I love it. This is I think we
Okay, I think
should
one last one and
wind down, but
I have a 5-minute question.
Yes. You're gonna get
So no, it's just a comment. I think a little bit of the confusion is that we're using for both the spin group and the magnetic group the same notation for a tensor that is fundamentally different. For the spin group, the tensor has two elements. There's two elements that are the spatial coordinates, and the other element is just lives in spin space. So it's so in the spin group, the tensor has one component that is a vector in spin space, and two components that are you can't use 3 indices because that is assuming that your magnetic field has certain directions in momentum space, in spin space. In real space. Thank you. So that's the problem. I mean, if we can't call lambda x, y, z something in spin space and magnetic space. We should call lambda x, y with a vector showing that it can be for any magnetic field applied. Doesn't need to be along z.
This is not true.
It is true.
This is only true in a non-relativistic.
But that's exactly what I'm saying.
But this is all relativistic.
But you are trying to distinguish, that's the confusion that I'm trying to, I'm not saying it's your fault. I'm just trying to say that the confusion, thank you. Well, we were confused here, so there is a confusion. Both of us are confused, so I think that qualifies as confusion. It's because we are using notation for magnetic groups to talk about things that are in spin group which are non-relativistic. That I think that's all that is. It's just a matter of finding a notation that is consistent.
I think we are converging
Okay.
nicely.
Can I make a?
Yes, you may of course respond.
I'd like to make a point here that first of all, it's true that in the non-relativistic limit, m is not an independent vector; it's parallel to L. So if we stick if we stick to the non-relativistic limit, there's really one component along n. But that's not all that spin point groups tell you, because here you have L dot m invariants. Those are not at all with m parallel to L. They're off-diagonal components, and those absolutely do depend on the crystallographic orientations of everything.
It can't, right?
It can't. It just can't.
What do you mean it can't?
Depends on the direction, then it cannot be. I'm sorry.
That's just how it is.
That it can be what? What?
Exchange interaction means that L
It doesn't come from exchange interaction.
It does.
It's spin orbit.
It has to.
What?
If my field cares if it's being applied along X, Y, or Z, it means that
The field.
I'm not
Wait.
using.
Wait a minute. Which field?
Magnetic field.
There's no magnetic field
Doesn't
applied.
matter. You can
So
apply strain. I mean,
You
it's
talk
the
about
same
M. You talk about M,
Yeah.
right? Okay. So what's the point then?
The point is that if M depends on the direction that it is,
Yeah.
it cannot be non-relativistic.
It's not non-relativistic. I'm not saying it's non-relativistic. It is relativistic.
The non-relativistic part.
Okay. So you're only talking about this.
This has been an
Then,
absolutely
then this has
gorgeous
nothing to
discussion.
do. Then this has nothing to do with this slide.
Good. Okay, good. I think we have many wise things have been said. We meet at 10:15, right?